can start fundamental physics. Thanks, Misha.
Thank you, Martin. Thank you very much. It's a great pleasure to be here. I'm going to talk today about cosmology and specifically mostly about the theory of inflation, which is the primordial accelerated expansion of the universe that supposedly took place before the standard model physics took place. So the idea of cosmology really was conceived about 40 years ago, back in the day when cosmology was an extremely speculative field. Now it's extremely precise. It's a field where 1% error bars are standard. So that's why in my talk I'd like to start with some facts, well, 5 plus 2 facts about cosmology that are unquestionable, that are precise facts, that hopefully will help me convince you that these facts make inflation inevitable. And then once we accept inflation and combine it with some insights from high energy physics, then it will give rise to very rich, very interesting phenomenology in terms of the testing the particles at very high energies that could be as high as 10 to the 14 GeV via the approach called the Cosmological collider. And then in the second half of my talk, I'm going to discuss the observational status of the constraints on inflation and the Cosmological collider, and also how we can improve this observational constraints using the advanced modeling of nonlinear structure with insights from field theory, as Martin mentioned. Right. Fact number 1, they are cosmological fluctuations. In cosmology speak, fluctuations are distributions of stuff on large scales. Different kinds of distributions that take place at distances about 1 billion light years. And these examples of these distributions include the temperature and polarization, the cosmic microwave background on the sky, galaxies, the distribution absorption line in the spectra of distant quasars and galaxies, etc. We have many examples of these distributions. And the fact number 2 follows that these fluctuations that we observe are primordial. By primordial, in cosmology speak, we mean that they were formed before the hot Big Bang stage. So the hot Big Bang is the end result of the extrapolation of the evolution of the universe backwards in time. So we know the universe is expanding. If we reverse this, we'll see that many billion years ago, the universe was in a very hot, in a very dense state. So if we apply this logic now, well, this state is called, well, basically the Big Bang, and then the expansion of the universe, can be thought of as the result of some sort of explosion. So let's apply this logic to the CMB maps that we see. So the cosmic microwave background fluctuations, they were formed as a result of recombination when the universe was about 400,000 years old. So let's extrapolate back the evolution of the universe, and we can draw a simple study diagram that shows us the evolution of the CMB before the recombination. And if we do this exercise, we'll see that the different patches of the sky that we observe, actually they were never in causal contact with each other, which is very strange because they look identical. So this is the first sign that these fluctuations were formed before the standard Big Bang evolution. And to make our discussion more precise, we can talk about the correlation properties of the cosmic microwave background radiation, so the temperature fluctuations. So the temperature fluctuations they represent a Gaussian random field. So all the information encoded in this field can be characterized by the 2-point function, the power spectrum, that itself is a function of the harmonic multiples or the angles on the sky. And if we compute this power spectrum based on our observations, we'll see that we have correlations even on very large scales, even on scales of the order of tens of degrees on the sky, which is, again, very puzzling because the different patches of the sky we observed, they never had the chance to talk to each other, and yet they appear 100% correlated. So obviously, the only way to reconcile this fact with theory is to assume that these correlations must have been imprinted before the Big Bang. Fact number 3, these fluctuations are adiabatic. By adiabatic, we mean that all these fluctuations on large scales